Hello everyone and welcome to the Life in the Universe pandemic series. So this is a set of short talks about things to do with life in the universe that I think are interesting and I hope you do as well. So today I'm going to talk about this question: is there life in extraterrestrial oceans? Now, a few decades ago, this would have been a quite outlandish question to ask. Could there be extraterrestrial oceans, even extraterrestrial oceanography? And we now know that there are oceans out there in the outer solar system. A few decades ago, most people assumed that moons were a bit like our own moon, essentially made of rocks, rocky worlds, rocks that coalesced from the protoplanetary disk from which our solar system was formed, or in the case of our own moon, from a giant impact slightly later, and that these other moons elsewhere in the solar system must also be made of rocky materials. But then in the late 1970s, the Voyager spacecraft headed out to the outer solar system, and what they saw was something very different. They saw that Europa, the moon of Jupiter, was covered in an icy crust that was very white, very different from grey rock. And they also saw Enceladus, the moon of Saturn, which was also strangely white and icy. And as early as the 1980s, people began to speculate in scientific papers that there could be oceans beneath the surface of these moons. And this really changed our thinking about the possibility of places in the solar system that could be habitable. So do they contain life, these extraterrestrial oceans? Well, first of all, we have to ask ourselves, how is it that these frozen moons out in the solar system can have oceans in the first place? Because out there around Jupiter and Saturn, temperatures are very, very cold, and these are considered to be the frozen wastelands of the outer solar system. On our own planet, by contrast, the atmosphere traps heat, warms the surface of our planet, and of course we can have liquid water oceans sustained by the solar radiation of the sun. But much further out in the solar system, where the sun's radiation is a lot less, we would not expect to find these liquid water oceans. These oceans are sustained by very different processes, and mainly by tidal buckling. So if you think about the moon Europa, for example, the moon of Jupiter, it is in orbit around Jupiter, and it's tidally interacting with the great gravitational forces of Jupiter and being interacted with by the other moons of Jupiter as well: Ganymede, Callisto, Io, the other Galilean moons. Europa is in resonance with these other moons. And what that means is that the core of Europa is constantly being buckled by these gravitational interactions between the moons and Jupiter. And the best way to explain that is using this spoon. So if you look at this spoon and I bend it, I can feel the middle of the spoon beginning to get warm. So the energy that I'm putting into bending the spoon is being released as heat energy in the atomic structure of this metal. The same thing, same principle at least, in the core of Europa, where the great gravitational interactions are buckling the interior of the moon and releasing heat, and that heat is melting the ice and generating an ocean beneath the crusty surface. If it was in direct contact with space, of course, the ocean would instantly freeze in the freezing conditions, but that layer of ice traps the ocean beneath it. And this is the case for Enceladus as well, one of the moons of Saturn. And there's good evidence that there's oceans there. For example, Europa has an induced magnetic field, and the Galileo spacecraft was able to look at that and also examine the surface of Europa. And that induced magnetic field tells us that in the interior of Europa there is some conductive material of some sort that we think is a salty ocean. And there's other evidence besides for an ocean beneath the surface of Europa. The same is true with Enceladus. We can gather indirect evidence for an ocean, but in the case of Enceladus, we can actually see plumes being erupted from the interior of that moon. The Cassini-Huygens spacecraft that went to the Saturnian system in the early 2000s saw these plumes erupting from the moon in these fractures at the south pole of the moon called tiger stripes. And these plumes can be seen with the sun in the background very clearly coming out from the interior of Enceladus. So much more direct evidence for a subsurface ocean. The question is, could these oceans contain life? And what we need to do is to think about the requirements for biology, the requirements for life. So let's have a think about Enceladus. So Enceladus is an interesting moon. It's about 500 kilometers in diameter. As I say, it's erupting plumes, and those plumes seem to be contributing to the E-ring of Saturn's ring system. So Enceladus is embedded in Saturn's ring system. So what do we need for life? Well, we need a source of liquid water, and those plumes turn out to be made of water ice. They're not made of some strange exotic chemistry or solid ammonia or something else. They're made predominantly of water, and that tells us that they are coming from a subsurface liquid water body. And we need liquid water, at least in all known life, as a solvent to carry out all those biochemical reactions, to move the reactants around. So there's no shortage of water. We think that the liquid beneath the surface of Enceladus, in fact, we know that the liquid beneath the surface of Enceladus is liquid water. So that's the first requirement met. We also need elements with which to construct our life form, and there are 6 basic elements that are needed, at least in all known life, and they're sometimes referred to as the CHNOPS elements, and that strange word is made up of the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CHNOPS. So elements other than those are needed by life, like iron and transition metals, magnesium as the case may be, zinc in some organisms. But those 6 elements, if you like, form the chassis of life, the life that we know. We need those 6 elements. So where would we get CHNOPS elements from in Enceladus? Well, let's start off with carbon. We know that there's a carbon source in the form of carbon dioxide gas, which we find in the plumes. And the Cassini spacecraft was also able to measure organic material, carbon-containing compounds in the plumes. So there's a plentiful supply of carbon atoms. There's also a supply of hydrogen atoms in the form of water, and hydrogen atoms in those carbon-containing organic materials as well. So that's in no short supply. Nitrogen, moving on with our CHNOPS elements, nitrogen is found in ammonia, which has the chemical formula NH3. The N is nitrogen, ammonia is a potential source of nitrogen, and we find that in the plumes as well. Oxygen, there's plenty of oxygen, for example, in carbon dioxide, CO2. That's got oxygen atoms in, and there are other compounds as well that have oxygen atoms, so no shortage of those. Phosphorus is a bit more enigmatic. We've not directly measured phosphorus in the plumes of Enceladus, but we suspect that there would be phosphorus if the core of Enceladus is made up of materials like basalt or ultramafic rocks that make up planets like the Earth, rocky worlds. Then we would expect phosphorus in the form of apatite, which is a calcium phosphate mineral. So we can indirectly infer that there should be a source of phosphorus. If the core of Enceladus is instead made of meteoritic material, like carbonaceous meteoritic material that is some of the most primitive material in our solar system, we find a mineral in there called schreibersite, which is also a phosphorus-containing mineral. So although we haven't directly measured phosphorus, there's good reasons to suspect that it would be there. And finally, sulfur. There are gases like H2S in the plumes of Enceladus, and there's probably sulfate ions in the oceans as well at some low concentration. So there's probably other sources of sulfur. So when we think about the CHNOPS elements, there's good reason to suspect that we have all of the requirements. They've either been directly measured, or where they haven't, we've got good reasons to think they might be there. But we need more than just elements to build life. We also need an energy supply. And you and I, we eat our sandwiches and we burn them in oxygen through aerobic respiration, and we release energy from these sandwiches to power biological processes. Where would the energy come from on Enceladus? Well, hydrogen gas has been directly measured in the plumes of Enceladus, and carbon dioxide has also been directly measured. And we can put hydrogen gas together, carbon dioxide, to release energy in the process called methanogenesis, production of methane. Methanogenesis, genesis of methane. Methanogenesis is one way in which microbes can release energy from hydrogen and carbon dioxide. In fact, it's thought to be a very primitive and ancient form of making energy. We see it here on the Earth, and it would be a plausible way of making energy or releasing energy on or in the interior of Enceladus. So we seem to have some plausible energy supplies as well. Those organic materials that have been detected and in Enceladus, maybe they could be used in fermentation. and you may be aware of that process for making beer or pickled vegetables. Fermentation is also a primitive way of getting energy out of organic compounds, and maybe that would be a way of making energy in Enceladus, and so on and so forth. So when we look at all the requirements, liquid water, Chernop's elements, and energy, we seem to think that Enceladus has all the necessary ingredients for life. And the ocean itself does not seem to be very physically extreme. We think that it's mildly alkaline. There's no iron or metal or other salty ingredients in that ocean that have been measured that would suggest that it is toxic to life. The big question, of course, is even if it is habitable for life, has it got life in it? And that's something we really cannot answer at the moment, partly because we don't understand how life originated. Do the conditions that gave rise to life on the early Earth apply to Enceladus? Are the sorts of environments where we think that the origin of life occurred on the Earth, are those transposable to the interior of Enceladus? Did Enceladus have conditions deep in the ocean or in its core to give rise to life? And if the answer to that is no, then Enceladus might well be suitable for life, but it may be uninhabited. It may simply be devoid of life, even though it could theoretically support life. The best way to answer this question is, of course, to go to Enceladus and get some of that plume material and look at it right there, or bring it back to the Earth and look directly to see whether it contains life. And that's a very thrilling prospect, simply because it's so possible. We know that there is a subsurface ocean throwing material out into space. We just have to get a sample, and then we can actually get an answer to the question, is there life on an extraterrestrial planetary body? What about other places? Well, Europa is less well understood. There are not plumes being erupted from the interior that we could fly a spacecraft through, or at least plumes that we think are substantial. Some people think they have detected plumes coming out from the interior of Europa, water plumes that have been seen, for example, by the Hubble Space Telescope. But certainly there are no plumes that we've been able to fly a spacecraft through at the moment, but maybe in the future that will change. But what it does mean is that at the current time, we have much less information on the interior composition of the European Ocean. There are other places we might think about exploring, like Ganymede, the moon of Jupiter. This is an interesting moon because people think that the ocean might be sandwiched between layers of high pressure water ice. And that could be a disadvantage for life, because in Europa and Enceladus, the ocean is in contact with a rocky core, which might be allowing elements and minerals to dissolve in that water and generate the requirements for life. But if the ocean is sandwiched between high pressure layers of water, then it's going to be rather stagnant. It's not going to be mixing with rocks and generating energy supplies. So the ocean of Ganymede may be a lot less suitable for life. There are other places that we could examine for life as well. Ceres, one of the largest asteroids, or the largest asteroid in the asteroid belt, we think has salty water beneath its surface. Is that salty water habitable? We certainly see salts on the surface of that moon, ammonium salts, carbonate salts, which on the Earth would not preclude life. So we can't say that life is possible in Ceres, but we can certainly say that the briny solutions that appear to be there are not necessarily detrimental to life either. So that is another frontier that we could explore. So at the current time, is there life in extraterrestrial oceans? We don't know, but we have some tantalizing locations to go and answer this question. Lots of different possibilities, probably lots of different chemistries of oceans that we can go and explore. And in the next few decades, it will be possible to get samples of these oceans and look directly in these waters to see whether extraterrestrial oceans contain life or not. That is possibly one of the most thrilling frontiers in astrobiology, at least within our own solar system. Thanks a lot for joining me. Take care of yourselves.